Hello, everyone. First of all, I need to apologize for the urgent meeting last week, which makes us rearrange the lecture. And also, it has been 3 weeks, including the Chinese New Year break, since we last met. Okay, so I hope that you still remember something from the first 3 weeks, because today we are starting with the online algorithm, but we have something not covered yet, right? Okay, and also today I will release the last in-class exercise for the first half of the semester. And then after completing that, you may feel free to upload that when you see the upload option available. Okay, now this is about the in-class exercise. And there's also something about the assignment. As I announced in the Canvas, the first assignment will be released in week 4, but because we didn't have lecture in week 4, we'll release it in week 5, which means this week, and we will do it tomorrow, latest tomorrow afternoon. You will see the first assignment. And also, the assignment will be relatively more difficult than the exams, because the assignment you have more time. You can think about various solutions, but for exam, it's not possible. So basically, the midterm and the exam questions, they will be relatively easier compared to the assignments. But of course, on the other hand, there may be 1 or 2 challenging questions in the exam, which is used to differentiate the higher tier of the class. Okay. So let me share the screen. Okay. Just bring up the chat. Yeah. So just to briefly review what we have talked about in the beginning of this semester. Now, basically, we reviewed the standard algorithms, including dynamic programming, greedy, and also divide and conquer, right? And then we go into the realm of the approximation algorithms, which try to compute some solution which is not optimal, but can be proved to be very close to the optimal solution, right? So this is approximation algorithms. And then in the last lecture, we talk about online algorithms. So for online algorithm, it means that your algorithm does not know the whole information. And then you need to make decision whenever you see some new input. And then because of this, because of the inadequate information you get, you cannot get the optimal solution. So that's not caused by the computational aspect, right? Because you can assume that you have arbitrary computational power, but still, because of lack of input, you still cannot do very well. And therefore, in online algorithms, we use the so-called competitive ratio, right? We do not say approximation ratio, we say competitive ratio to, measure how close your solution is to the offline optimal solution, right? Okay, and then in the end of the online algorithms slide, we will mention something which has something to do with probability, okay? Now remember that when you see the course syllabus of our course, you will see some prerequisites, and actually one of them is probability, right? Okay, so, and you can expect that, we will use probability very likely only in this lecture, okay? Although in game theory, we will also very rarely use probability, but the major part of probability will appear in this lecture, including this part in the online algorithm and also the next slide, okay? Now let's just briefly review what we explained last lecture about the very famous secretary problem, right? Now in secretary problem, we are trying to select one candidate out of n possible candidates, and then your target is try to select the best one out of the n. But because they arrive one by one, and you need to make decision whenever you see a new candidate, then that makes the problem a bit harder, because you don't know when to make your decision, right? When to decide, okay, I should select you, and then finish the whole process. Okay, so it's just like this secretary problem can be used in many situations, right? Not only secretary, it can also be some kind of a job offer, right? Or well, some further opportunities in your life, right? So you need to make decision about which candidate you will pick, right? Okay. Now, just to see, well, actually, I myself already forgot whether I explained any algorithm for this secretary problem in the last lecture. So can anyone remind me? Yes, okay. So basically, we are somewhere here. So this is this one we covered, right? So we always take the first candidate, right? And then the chance that this candidate is the best is only 1 over n, because we are working through all the possible arriving order of those candidates, right? So among all of them, the first one being the best, the chance is 1 over n. Okay, so this one we covered. And then this one, strategy 2. So what is strategy 2? Okay, strategy 2 said we try to adopt something. We say, okay, we will skip somebody, right? So we look through the first half candidates and do not select any one of them. But they will be used as a benchmark, right, to help us decide for the second half. All right. Now, you can see that the probability of finding the best candidate in this case is what? So because in this strategy, we are selecting the first candidate, which is better than the first half candidates in the later half, right? So you use the first half candidates as benchmark, and then say, okay, from now on, and whenever I see somebody who is strictly better than all the previous n over 2, then I will select this person, right? So so I remember that we have explained that probability, and that's where we stop, right? So this probability of finding the best candidate is that, well, first of all, your best one should be in the second half, because if it's in the first half, you will not select it, right? So you will just skip it, then you lose, right? Okay, so the one probability is the best candidate is the second half. And also there's another requirement. The second best should be in the first half, all right? Why second best should be in the first half? Well, because if the second best is in the first half, then using that as a benchmark, in the second half, you will only choose the best candidate, right? You only choose the best one, because nobody else can be better than the second best. Only best one can be better than second best. Well, but there is one inequality sign here. It's not equal. It's not equal. Well, so can anyone tell me why it is not equal? To me, it seems that it's just exact correspondence, right? It's equal probability. It just equals the first half contains the second best, and the second half contains the best. Okay, so Xuezhen said that the second best can be in the second half. Okay, well, yeah, that's possible, but it's not complete. Okay. Okay, I'm reading your answers now. So one thing, if I draw a line, right? So first half, somebody here, right? Now suppose, very good. Okay, so Jingfeng said, but the best appears before all others are in, right? Okay, so basically that means the first half, actually I do not need them to be to contain the second best. Why? Even if they are very bad, right? Even if this group are really bad, I can still have the chance that the best one is here, which is the first one in the second half. So whenever you see this one, oh, it's better than the previous half, so you select it. So there is still a chance that the best one is selected, even if the second best is not in the first half, right? Okay, yeah, very good. Wing Chong, you are getting the point. You are hitting the point, right? So basically, the second best is after the best one, right? So basically, you see the best one first, and then second best, but it's still okay, right? But anyway, we have some kind of I remember someone mentioned of some kind of worst case, right? So basically, this is larger than or equal to, which means, well, as long as these two events happen, right, you will always succeed in selecting the best one. Okay, so no hurt, right? You just use this one as a lower bound, right? You say, okay, at least I can select this this times that. With this probability, I'm able to select the best candidate, right? Although in reality, it may be larger, right? Okay. All right, so this will give us the probability of quarter, right? Now, let's move on. Now there is a strategy 3. So this third strategy needs some kind of a intricate analysis. Okay, no longer that easy to say, oh, certain probability I can well select the top candidate with the highest chance. Okay, so the third one basically says that throwing away the first half seems a little bit waste, right? So it asks, well, maybe we can throw away a few less candidates so that, well, we have a higher chance of getting the top candidate, right? Okay, so the strategy says, well, we interview the first n over e candidates. So you see that e is a natural number, so which is a 2.7 something, so which is larger than 2, right? So basically you select about a quarter of the candidates, and then for the remaining, you will select the first one, which is better than all the first n over e candidates, right? Okay. Well, so then the probability of finding the best candidate will be 1 over e. Okay, so here today we are going to analyze how to compute that so-called best strategy. All right. Okay. Now, firstly, we have some observation. Now, one thing is our algorithm will never pick an element which is not the best so far. All right. Okay, so this is one thing which may not be obvious. Well, but well, remember our target is to select the best, right? So if you do not pick the best one up to now, you definitely fail, right? Even if you say, oh, maybe the best one is I already throw it away, right? And then I pick this something which is slightly weak, but that does not help us because we are not trying to maximize the quality of the candidate, right? We are trying to maximize the probability that we select the best one. So the algorithm must pick an element which is best so far, all right? So this is something you have to follow. Okay, now we compute one probability, and this probability we call it Fi. Okay, so this Fi says what? Okay, now because we are choosing a candidate which is best so far, so this is a condition, right? I must be the best so far, right? I pick the ice candidate, right? Now, with this condition, if I is the best so far, then what's the chance that I is a global best? Now, this is the probability that we'll succeed if we pick an ice element which is the best so far, right? Okay, and how to compute this probability? Well, so according to the way you compute the conditional probability, then this is equal to the probability that the ice item is globally best divided by probability that the ice is best so far. Okay, so this is the by definition, right? By definition of conditional probability. Okay, now ice item is globally best. We know it, right? Every position it's globally best. The chance is 1 over n, right? It's this 1 over n, right? Okay, now what's the chance that ice one is best so far? Well, this is a bit tricky, but it's not that difficult. So we have a 1, 2, 3, 4 until I, right? We say, okay, among the first I elements, what's the chance the last one, the ice one, is the best? Well, it's just the same as what? You narrow down your focus to the first I elements, okay? You have I elements only. And what's the chance that the ice one is the best among the I elements? Well, easy, right? It's just 1 over I, because the best one can be anywhere. can be position 1, position 2, right, until position I. So, well, it's the 1 over I chance that the last one, ith one, is the best of the first I elements, right? Okay, so this is 1 over I. Now, overall, it will be I over n, right? Okay, so this is fi. Now let's continue. So this fi function, you see, it is an increasing function, right? You have a larger I, of course, you will have a larger I over n. You have a higher chance. For example, you say, okay, I choose the last element, all right? Now, if you choose the last element is the best so far. Of course, it's the globally best, right? And then this probability becomes 1. So fi is an increasing function, right? Okay. Now, let's define another function, which is called gi. Now, gi function, it means the probability that you use your very good strategy or globally best strategy, or well, so basically it's the best strategy, the optimal strategy, right? Use the optimal strategy, but you can only select items from item I on, which means you throw away the first I minus 1 items. So you have a long list. You say, okay, if I do not allow you to select these, I only allow you to select from item I, okay? And then, but selecting from item I allow you to be very powerful. You are able to know who is the best, and then you can just accurately find that best and select it, okay? So if you have this power, gi means the probability of choosing the global best starting from item I, okay? Well, now you know gi is a non-increasing function, or yeah, to be accurate, it's not increasing, but well, generally we can also say it's decreasing, right? Somewhat decreasing, okay? Now, because you have a larger I, that means you have less candidates, then of course, the winning chance becomes less, right? So for I, you have this many candidates, but if you start from I plus 1, you only have this many candidates, then of course, your chance of selecting the best one will decrease, right? Okay. So there's one easy argument saying that, well, if it's not, if it's increasing, so if gi is less than gi plus 1, then it's a contradiction because, well, then for gi, you can simply say, for item I do not want it. I do not select it. I just give it up and then adopt the strategy of gi plus 1. So I can do as good as gi plus 1. So basically, this explains that gi function is somewhat decreasing, right? It will never increase. Okay. Well, so what's the optimal strategy? So optimal strategy says, maybe we should do the following, because you see, fi is increasing and gi is somewhat decreasing. So basically, at every time I, you are facing a choice. What's this choice? The choice says, if I select this item I now, I will have this probability to get the best one, right? If I give it up, if I say item I do not want it, and then that means you have some probability of adopting this, right? You have a probability of adopting gi plus 1 because you say, okay, I need to decide whether, so if I see item I is the best so far, should I accept it? If I accept it, then my winning chance is this. If I throw it away, my winning chance can be this, right? Can be gi plus 1. Okay, so whenever fi is less than gi plus 1, then you should somehow skip item I because, well, skipping will give you more benefit, right? Okay, so, well, any question up to now? It's generally okay. So let me just finish the whole thing and let's see whether the majority of you can get the idea. Okay, so now what do we do? So how do we analyze? How do we find this I? Because our target is to find I, right? Okay, so let's see. Now suppose we reject the first tau items, all right? We reject tau items. Then the probability that we succeed in picking the global best becomes this. So what's this? when we look at the expression, you see that, well, because you throw away the first tau items, so you can only select items from tau plus 1 up to n, right? And for each of them, what would you do? You say, okay, for each of them, let me see the probability that this item is global best times the probability that the best of the first t minus 1 items is in the first tau positions. Okay, so what does it mean? Well, we have tau. So many items you throw away, right? You do not select it. And then you say, okay, for any position here, if this is the best up to now, I select it. How to make sure this one is the best globally, right? Or how to make sure that this one can eventually can be selected by you, right? Okay, now, so it says that the best of the first t minus 1 items is in the first tau positions. Okay, because you know the algorithm will not compare this one with any of the people here. They will only compare a candidate with all the candidates you throw away, right? So you need to make sure the best one of this group, right? The best one of this group is somewhere here. Okay. So if the best one of the first t minus 1 items are here, then you will select this one. Okay, so the probability will be multiplied together. Tth item is global best times the probability that the best of the first t minus 1 items is in the first tau positions. Okay. Well, so I guess that I didn't mention one thing which is critical, because actually this condition is trying to make sure this candidate, the tth candidate, will be selected. It will not be somehow hijacked by some previous elements, right? So remember, we say that whenever you see somebody better than the tau elements, you select it, right? So if the best one among the t minus 1 elements is somewhere here, then they will hijack. They will say, okay, I'm already better than the previous tau. I will be selected. So then you will never have the chance to reach t. Okay, so the second condition actually is doing a job to make sure position t will be selected. Nobody before him will have any chance to be selected because they are not better than the first tau candidates, right? Okay, so I guess this is about the time that I do a survey. Okay, so let me just issue a survey about how many of you understand the reasoning about this probability expression. Okay, so I can see that the majority of you got it, but still quite some of you didn't get the probability. Well, so basically, well, it is fine to review it a bit later. All right, so for now, let's just use this one for a moment, okay? Because I know that the probability analysis will be sometimes quite tricky, so it's not possible to understand it, understand every part right on the spot. Okay, so so basically, we are trying to sum up the probability of the algorithm to select best, and this best can be in any position, like tau plus 1, tau plus 2, up to n, right? For each of them, right? For each of them, as I drew earlier, and maybe I will draw again here. For each of them, the probability is something like this. You have tau candidates you throw away, and then you say, okay, my target is to select this guy, okay, because this is the global best, right? This T's one is global best, but I want to make sure nobody here will be selected because they still have a chance to be better than the previous tau, right? If they are better than the tau candidates, they will be selected, not T. So we are trying to say, okay, what's the chance that nobody here will be selected? So this corresponds to the probability in the second half, all right? So you have to make sure in the first group, from beginning to up to now, up to here, the best one should be thrown away. It cannot be here, all right? If they are there, if they are here, they will be better than the previous tau elements that will be selected. So you have to make sure the best one is somewhere here, right? In the thrown away part. That's why we have the probability in this way, right? Okay, so now I will erase this part to make our reading of the next statement easier. Okay. Now we try to compute this result. Okay. Now you can see that this probability is the following, right? T item is global best 1 over n, right? Because any position is global best, the chance is 1 over n. And then best of first T minus 1 items is in the first tau positions, okay? So the best one is in this range. The probability is tau over T minus 1 because altogether you have T minus 1 items, and then you say, as long as you are in the first tau, it's okay, right? So it has this chance to be in the first tau elements. And then when you multiply them together, you see tau over n, you take it out. And the remaining is 1 over T minus 1. Okay, so it's adding up 1 over T minus 1 from tau plus 1 to n, which means it's adding from tau 1 over tau to 1 over tau plus 1 plus etc. Until plus 1 over n, right? Yeah, until it's 1 over n minus 1. 1 over. Yeah, okay. So there's one minor term, but okay, it's not affecting the overall calculation. Okay. Now this one, remember that last time we talked about the so-called harmonic function, right? It's 1 plus 1 over 2 plus 1 over 3 plus and until plus 1 over n. This will be equal to ln n. So harmonic number, right? So it's hn. Hn is harmonic number, and then the value is roughly ln n. Okay, so if you do the addition from the middle, then it's just the hn minus h tau minus 1. Okay, so you add from 1, right, to here. Now, firstly to 1 over n, and then remove the beginning part, or remove this part. Okay, so it's hn minus h tau minus 1. Okay, well, so next. So this value is the g tau plus 1 value. So because we are throwing away the first tau items, and then we try to select the best, right, the best candidate in the remaining piece. Okay, so what's the chance it is winning? Well, by definition, right, because now we are talking about the best strategy we can adopt, right? So basically, it will be g tau plus 1. Okay, and then we compute, right? So g tau plus 1 is something like this. We calculated it, and then f tau, you know, it's n tau over n, and then you know the first moment when f tau is larger than or equal to g tau plus 1 is given by the smallest value tau, such that this difference is less than or equal to 1. Okay, so whenever this is less than or equal to 1, then g value will drop below this f value, right? Now, because you have a common term here, tau over n, you also have a tau over n here, right? So you need to make sure the difference here is less than 1. Whenever it is less than 1, then g function will be smaller, and then you stop, right? So by calculation, it's easy to see, right? If you have this kind of condition, tau will be roughly n over e. Now, I will not go into that detail about computation. I guess you can figure out why the tau is n over e. And then you will be able to compute, okay, if the tau is n over e, then this value, tau over n, will be roughly 1 over e, right? Okay, so basically the chance of success is 1 over e, right? Okay, so that corresponds to our earlier so-called best strategy, right? The best strategy says you should throw away so many elements, right? And then your chance of winning is 1 over E, right? Okay. Yeah, so any question up to now? Okay, so basically here you can see that this is the simplest secretary problem, but well, in reality, you may have more complicated ones, right? You say, okay, maybe I need to consider what's the chance that if I can pick 2 candidates, right? What's the chance that I pick the top 2? Well, you have many meaningful variants of this secretary problem, but for the purpose of our course, we are only introducing the basic one. Okay, I guess that will be sufficient for let you know the existence of the problem, and then if some of you are interested, you may explore further about different variants. Okay. Yeah, and then the second part of the online algorithm in the end of the topic will be the so-called profit inequality. So this also has something to do with probability. All right. So profit inequality is talking about the following thing. You have n random variables, x1, x2, up to xn, right? And then we know their distribution. Let's say, for example, somebody is Gaussian, somebody is normal distribution, etc., etc. Okay, but you don't know their values, right? You only know their distributions. Now, these realization of these variables, they are revealed to you one by one. Okay, so C1 values, C2 values, etc., etc., right? And then we want to find a strategy which says, okay, when I see the value of xi, and also all the values before it, right? And then decide, okay, I should choose I, right? And then if you choose I, you will get reward xi, and then the whole process will stop. Okay. So now, we can also say, well, maybe we can just skip this item. I do not select it. But if you skip it, you will never be able to come back again. Okay. So if you either select this item or give it up. All right. It's just like secretary, right? So it's similar as secretary, but now our target is somehow uncertain, right? Because for secretary, the values, the order is not known, but the absolute value, they're all known. But here, you don't even know the value. You only know distribution, right? And these values, they will be realized one by one. You don't know you don't know, well, exactly what value you'll see in the next item, right? In the next item. So what's your target? The target is to try to maximize the expected reward or expected X, right? Okay. So in other words, this is the optimal. So if you have n values, x1 to xn, you take a max, we call it x max. The optimal one will be able to always get x max, okay? But then the prophet, which is this wizard, right? He knows everything, okay? And then he will be able to get the so-called E x max, okay? So because x max is also a random variable, it also has an expectation. So the prophet is able to, well, so these two prophet is the same pronunciation, but different meaning, okay? So this prophet, he is able to get E max, Ex max, okay? So the random variable X max, the expectation of it, you get it. But for ordinary people like us, we cannot, right? So we cannot get more than Ex max, and actually not even close. We can only get a small amount. Then the question is, how much can we get, right? Okay, so now I would like to do a survey again. So about the problem definition, is it clear? What you can do and your target. I see a question. Yeah, so again, the distribution seems similar. Well, it may be because of the understanding of probability. Well, I guess yeah, I will first answer a question raised by Ziyao. Okay, so Ziyao asked, as the distributions are already known, why can't we just choose the largest EX? Oh, good question. Okay, very good question. Actually, we'll come to that very soon. Okay, so you have one variable which has a very good expected value. Okay, then you say, okay, I just choose this one. I just choose that X. Well, that may not be very good, but it's also not very bad. Okay. Now, the reason I guess you will see very soon. Okay. So this is so if you can only select a certain xi, for example, you say every time I should select x2. Okay. Every time should select x2. Then your strategy is the best. Okay. But now the question is, for different running or round of this experiments, you can select a variable at different position. For example, you say, okay, I see the first value to be 1, and then second value to be 2. Okay, so then I select second value. But if I see the second value to be 1 also, then I say, oh, then I will not select second value. I continue to the third one. So basically, you can change your decision based on the values you see. So I guess this is also why some of you still didn't get the whole story about the problem. Okay, so basically, you are trying to maximize the so-called expected reward. This expectation is taken over all the realizations of the random variables. Okay, so well, just to make my explanation a bit easier, now suppose every xi is a binary random variable, which means it only takes 2 values. All right. Okay, so for example, I say xi, it can be 0 or I. Everyone only has 2 values, 0 or I. Yes, you only know the distribution, you do not know the exact data. Okay, so let me, the example here is I'm trying to say is that so Xinyan is asking a question. Decisions are made before revealing its value. It's no, it's not the case. The decisions are made after you see its value. Okay, after you see its value, and not all the variables share the same distribution. They can have different distributions. So now I'm giving you one example. So this example says xi can take value 0 and I with equal chance. Okay, half probability it will be 0, half probability will be I. And then what's your strategy? You say, okay, my strategy is what? Whenever I see 0, I skip. And then whenever I see somebody which is not 0, I may take it, probably. Okay. Now, anyway, for this kind of distribution, there are many possible realization. For example, it can be all zeros, right? It can also be the first one is 1, all others are zeros, right? And then it can also be first one is 0, the second one is 2, and then others are all zeros. So basically, you see every xi has 2 choices of values, right? So altogether, there are 2 to the n different combinations of values. So the expectation, the expected reward is taken over all these 2 to the n realizations. Okay, you have so many possible realizations, and you try to maximize the expected gain you get among all these 2 to the n possible realizations. Okay, and then so let me just come back to the question about picking the best expected value. For example, you say, okay, I simply pick the xn. Okay, I do not look at any of the previous items. Okay, I just look at the last one. No matter what it is, I take it. Then you will get an expected value of n, right? N over 2, because you have a half chance this is n, and the half chance is 0, right? You get n over 2. So as I said, this may not be bad, but it's also not the best because, well, basically you, well, somehow sacrifices some of the, for example, if this value, okay, if the second last value, it realizes to be n minus 1, should you take it? Well, so actually, it's a pretty good chance. If you see this is n minus 1, I should take it because it gives me a lot of contribution, right? Now, because for the next one, if I wait for the next one can only give me expected n over 2. But this one already gives me n minus 1, which is better, right? So that explains what the, I guess it's what the Ziyao asked me, right? Okay, so basically, it's not always good to pick the xi whose expected value is the largest, because there could be some cases where at some moment, if I commit something, all right, for example, in the second last position, I take this item xn minus 1, and I already get n minus 1, then it's very good, right? I don't need to wait for one more item to come. If I wait for that item, the expected value I can get is only half n. It's not good. It's not better than my n minus 1, right? So that explains why it's not best to pick the variable with the largest expectation by itself, right? Okay, so this is the one thing. And then I guess I will ask another question raised by Yuqi. There are different distributions. Why not just consider them as random variables without distributions? Oh, okay. I didn't quite get your question. So because every random variable has some distribution, right? No matter it's continuous or discrete, anyway, they have distribution, right? Okay. So just want to poll again, all right? So try to see whether after my explanation, the understanding of this problem about what you can do and what's the possible good strategy, is it clearer now? So is it clear after my explanation? Oh, so very good to see that now a higher percentage of the students, well, got the point. Okay. Now, although not all, but I believe that now it's a bit safer to move on. Okay, thank you. Right. Now, actually, we only have a very small thing left. Okay. So basically, we are trying to analyze the probability, right? And then let's try to see what can happen. All right. Now, suppose we have two variables, x1. x1, its value is 1 with probability 1. Okay, so this WP means with probability. Okay, and x2 with probability epsilon, which is a very small number, the value is huge. It's 1 over epsilon. And then with a very big probability, which is 1 minus epsilon, the value is 0. Okay, so for these two, you see the expectation of both of them is 1, right? Okay, then what can you do? Well, so actually, expectation of both of them is 1, but expectation of E max, the X max, is close to 2. Why is that? So you see that E max, what is E max? So E max, when x2 is 0, E max is 1. It takes x1, right? When x2 is 1 over epsilon, E max is 1 over epsilon. So E max will be 1 over epsilon with probability epsilon, right? Okay. And E max will be 1 with probability what? 1 minus epsilon, right? So with this probability, E max will be x1, not x2, right? Okay. So with this probability, E max is 1. With epsilon probability, E max will be this huge number. Now they will add up to 2 minus epsilon, right? Okay. So that also explains that question, right? So why taking a single variable is not good, right? Well, it's not good enough, at least. Okay. Well, so now let's see what can we do. Okay, so since we know E max is 2 minus epsilon, then what can we do? Now we have some strategy. Say we can accept the first item. Okay, I just accept the first one. Now this will be give you a profit of 1, right? With probability 1, because well, your decision should be deterministic, right? Which means, well, you see item 1 is 1. It's always 1. So you only have two choices. Either you take it, right? Or you say, I skip it. I take the second one, right? You only have 2 choices. So basically, you only have 2 strategies. The first strategy gives you a profit of 1. The second strategy says, I pass the first item, accept the second. Then what do you get? Well, you just get 1, right? Okay. Yeah, so Xinran is asking, we can only approach Ex max, never get exact upper bound. Yes, you cannot get exact upper bound because, well, actually, this example is showing you, well, you cannot do better than 2 approximation, or, well, at least you cannot be better than half of the best you can get. Well, of course, it's better, but only slightly better, right? So basically, your performance will be very close to half, right? You cannot beat the half in a significant way, right? So this example shows, well, anyway, you only get expected profit of 1, but the best that can be achieved should be this. But then definitely this one is not obtainable, right? So it's there, it's there in theory, but you cannot reach it, right? So now actually, this is only, well, one example showing it's hard, but now we call this kind of thing a lower bound. So basically, nobody can do better than 1/2 minus epsilon approximation. Yeah, so Xiao, you're right. Ex max is some kind of offline optimal, right? Because we are talking about online algorithm. So offline optimal is some kind of benchmark. But, well, very unlikely it can be reached because, well, for online algorithms, almost impossible, right? You can only try to be close to it, right? Okay, and then this example, this hard example is showing you, well, this is well, very hard, right? You cannot do better than half competitive algorithm, right? So you cannot achieve a ratio much better than half, right? Okay, well, but now actually we also need some positive results, right? So can we really achieve half? So the answer is yes, we can. Okay, so this one shows you no online algorithm can achieve better than half competitive, but there is a strategy with expected reward reaching half Emax, and that will close the story. Okay, so let's see what the strategies are. So actually there are many, and we are talking about one of them. Now this strategy says we consider a distribution of Xmax. Okay, because, well, Xmax, you know the distribution because you know the distribution of all the x1, x2, x3, xn, right? Now, of course, there is a way to compute the distribution of Xmax. That's okay, right? So that one you can compute offline, no problem, right? Okay, so it's this, right? So the Xmax larger than C, probability that Xmax is larger than or equal to C is 1 minus the multiplication of the probability xi less than C. So if everybody is less than C, this will not be true, right? Okay, you multiply them together, everyone less than C. You do a 1 minus, it becomes at least one of them is larger than or equal to C, right? If at least one of them is larger than or equal to C, then Xmax will be larger than or equal to C, right? Okay, well, so you can compute this very easily. And then we take a so-called median of the distribution. So because it's a continuous distribution, so this median is somehow very ideal. It's just half, okay? So we try to find the value tau so that Xmax will be at upper side of tau with half probability, okay? So basically this gives us some impression, okay? So on average, or at the median bar, right? So the middle bar, what Xmax will look like, right? So how large this Xmax will be on average or in the middle, right? And then what do we do? Say, okay, now of course, well, because, well, we assume some continuous distribution. So at point tau, there's nothing, okay? So you cannot say, but for discrete one, it's a bit tricky. So for continuous one, it's easier, all right? Now the strategy is, whenever you see some value larger than tau, I take it. So this is a very, very simple strategy, right? You do an estimation. You say, okay, for X max, right? I know its distribution, and I cut it. I cut the distribution into equal parts. Okay, I try to see where the cutting value is, right? each side has half probability, where the cutting value is. And then I use that value as a reference or threshold. Whenever my value is larger than you, I stop. I take it. Okay, so this strategy can give us two approximations. So let's see why this is true. Okay, now imagine we are doing something. Okay, if x max is less than tau, the profit is just rounded up to tau. Okay, and if x max is at least tau, then we just accept that the profit is x max. Okay, so somehow we are well, being more lenient. We say, okay, I assume you are getting more profit than what you do, right? Okay, so Emax. So the computation of Emax will be this: tau plus Emax minus tau plus. So what does it mean? It means that, well, you get the tau, right? Because you at least get tau. Oh, so for Emax, right? Emax will get at least tau. And then when x max is larger than tau, it will get the extra part. So this one plus means that if it's larger than 0, it will be itself. If it's smaller than 0, it is just 0. Okay, so we are making the life of the optimal solution much easier. It says, okay, if your optimal solution x max is less than tau, I just give you more credit. I say, okay, I just assume you can get tau. Although you didn't get it, I assume you can get it. All right, and then if x max is really larger than equal to tau, I just credit the whole x max to you. Okay, assume that you can get x max. So how to compute this x max? It's a tau plus x max minus tau, right? Okay, so basically ex max can be upper bounded by tau plus this quantity. All right. Okay, and this is less than what? Less than or equal to tau plus the summation of all the expected values of xi minus tau. Well, because I'm being more aggressive, right? I say, okay, I will credit more quantity to this ex max but I don't know which one is Emax. Now I know some of them, right? So from 1 to n, one of them is equal to Emax. For the others, which are not equal to Emax, I also add it. I also add their non-zero or non-negative expectation, right? So for all the others, for example, xi, for example, there's kind of x2 minus tau, right? So if this is not Emax, this is not x max, I also, well, add this quantity to whole value. So by adding more, your optimal solution will be happier, right? So basically, I add more things to the right side, then that means, well, this value will be even larger, right? This value will be larger than the value here. Okay. Now, next one. So I will take a break after I finish this one, and meanwhile you can ask me questions. So algorithm, what is algorithm doing? The algorithm is the analysis is also easy. It says, okay, whenever your x max is larger than or equal to tau, I can always get tau. Why? Because the algorithm says whenever you see a value larger than or equal to tau, I take it, right? So if your x max is larger than or equal to tau, that means I can always see a value larger than or equal to tau. I'm able to take it. So what I gain is at least tau, right? So I can get at least tau times probability of x max larger than or equal to tau. But there's also some other thing I can get. Okay, so there's a plus here. So plus what? So plus says if I pick xi, okay, if I pick xi, then if xi is larger than tau, I can get a bit more than tau because, for example, xi is 2 tau, then I will get an extra tau, right? Okay. Now, but what's the condition that I can take xi? It must be true that any item before I, they are less than tau, right? Okay. So you need to make sure that all these xj, the realization of xj, actually this this can be capital, okay, capital X. So all the realization of xj, they are less than tau for those j before I. Because whenever I see a value larger than tau, I will take it, right? So if you want to take I, you have to make sure everybody before I, they are not taken, right? They are not taken. So they must be smaller than tau. So this is the probability, right? So probability that the earlier elements are not taken, but I's elements is taken, right? Okay. Now, I's elements are taken. If it's taken, then this expectation will be added. Okay. Well, so now I would like to say one thing. Okay. Why is this one larger than or equal to? Or is there some kind of a inaccurate computation? Yeah, so actually for me, I have one doubt. Now, although I know that this comes from very standard deductions. So there's one tricky thing here. Okay, so the tricky thing is here you only say j is less than xj is less than tau, right? Okay, but it seems that you didn't say anything about xi. Well, so there is some kind of intricate analysis here, which I guess I need to skip. All right. So here you didn't say I really pick I, right? Okay, you didn't say I really pick I because xi can also be less than tau. So then in that case, it's not picked. But in that case, adding this quantity doesn't hurt actually because this quantity is 0. If you do not pick xi, this is 0, so it does not affect the whole analysis. So I believe that there's some kind of a more detailed analysis needed, but for the purpose of the course, I guess we do not need to dig into much detail about this. So we only need to know the general picture about how you derive that half approximation. Okay, and then we try to, well, relax a bit. Okay, we say, okay, this probability, right? What's this probability? Everyone before I, they are less than tau. Okay, well, it's of course the probability here. This probability is larger than x max less than tau. Okay. So x max is the largest value, right? So largest value is less than tau. It will imply, well, all the things are less than, right? So all the things are less than. But again, here seems to be some issue. Yeah, I agree. So it should be x max of the first I items less than tau. That would be equal, right? So this one, probably, again, it has some kind of nasty things to be done, okay? So, but anyway, let's, well, this part is not the 100% proceedable, okay? But anyway, we'll first finish the whole thing, and we can discuss about what is wrong in the real probability analysis. Okay, now the last part is relatively easier because this is larger than or equal to, and then if you want to do so copy this one down, right? Copy this one down. This is here, okay, and then this part, why it becomes this? It's because tau is what? So now this will be the first. Now this one is definitely correct. Yeah, okay, then that's right. So this is because it's median, right? Because it's median, so the probability that x max is larger than or equal to tau is equal to the probability that the x max is less than tau. They are the same, right? Okay, so that will give you this. And then you can see that the whole thing here is the whole thing here. Am I circling the right thing? Yeah, so these two are the same, right? And then you know that this is half. So that means algorithm is larger than half of the EX max. Yeah, so Xinran is helping us to clarify certain deductions, right? Okay, so yeah, so basically, okay. Now because it's a larger than or equal to, right? So because this is larger than or equal to, so the first the items before I, they are less than tau. This event is a superset of everything is less than tau, right? Okay, so you said you have I have a small subset. Every element is less than tau. Okay, everything is less than tau. Okay, and then this probability must be larger than whole set. Everyone is less than tau, right? Because then you need to guarantee every element is less than tau, even outside one, right? So actually, the j-1 thing is not needed. So this one, this x max can be the whole thing. All right, so let me erase the writing here. So this x max can be the whole thing, right? Because this is a even stricter requirement. So earlier, I only require some elements to be less than tau, right? And now you require all elements be less than tau. So of course, that probability will be smaller. And that's why you have the last greater than or equal to sign, right? Okay, yeah, thank you, Xinran. You, well, helped me to address the problem. Okay, yeah, then we'll take a 5 minutes break and we come back to lecture 4. Okay, so meanwhile, feel free to ask questions. So one thing is, well, the probability analysis is really a bit, well, more challenging. It's also not the main focus of our course. I'm just trying to let you know that, well, sometimes for online algorithms, right, you are able to analyze some performance ratio for algorithms, right, using the probability analysis. Slide 34. So this one, yeah, it's a good question because later on, when we analyze GI, yeah, so when we analyze GI, we claim this is equal to G tau plus 1. Okay, so if this is equal, then it should be our strategy. I agree. Yes. Yeah, so GI, it should be our, so, okay. So I guess it should be our strategy in the best sense, because our strategy don't know what strategy it is, right? So it's also kind of a throw away something and pick a best, the first best one, or first one which is better than all the previous, right? So you don't know how many you throw away. So our strategy is not fixed. Okay, so it's the best of our strategy. Yeah, you're right. At the beginning of the course, after this class, you need to upload the 5 in-class questions. Well, so in-class question, the due time will be week 7. Okay, now it's week 5. In-class due will be week 7. And then, as I said, we already have one real in-class question plus tutorial 1 questions and plus 1 question today. Okay, so these will be all the questions you need to compile into one file and upload. So did I answer your questions? Yeah. Okay, yeah, thank you. Okay, very good question. How about deadline of OJ? So the deadline of OJ question, now they will be due at the same time as the 3rd assignment deadline. Okay, so basically it will be the end. But I guess it may not be that healthy to make it really to the end. So preferably, well, because the major algorithms we already cover everything in the first half. So please finish the OJ questions by midterm time, probably. Okay, but well, I will not make that harsh, the hard deadline, because anyway, this is a special kind of assignment. So well, if you have some other arrangement, it's okay to finish the assignment by the end of well, week 13, something. So the deadline for the last written assignment. Okay, because well, I believe that some of you need to think about whether you do this or assignment 3, right? So basically, you need to choose, and then it will be fairer after you see all the assignments, all the written assignments before you make a choice. But of course, for some of you think, oh, definitely OJ1 will be one of my assignments to be submitted, then you can just start earlier, all right? So that will also be safer. Okay, now this is the end. Let me share the new one. So this new one, well, definitely it will not be as hard as the online algorithm, not as hard as approximation algorithm, although the words seem a bit fancy, seemingly, well, they're fancy. I believe that this will be easier to understand. Yes, and then Doodleth asked me, is in-class exercise same as tutorial 1? So just to repeat once more before I start this new lecture. So in-class exercise is same as tutorial 1 plus 1 question I raised in class during week 1, I think, and also 1 question I will raise in this lecture. Okay, I'm about to raise it. So there are altogether tutorial 1 plus 2 questions. Okay, now let's start. Now we have known the approximation algorithm, also online algorithm, but there are also other types of analysis possible for algorithms, right? So some of them I listed here, for example, randomized algorithms, streaming algorithms, amortized analysis, and others, okay, and some other things. Okay, so I also referenced some online sites to prepare this one. But this one, I think that it will be, well, it will be something like if you didn't catch the idea of the sum part, it does not affect your understanding of the next part. Okay, well, but anyway, let's continue. Now here's a agenda. All right, so as I said, we will discuss 3 kinds of analysis, right? And also very briefly touch the so-called smooth analysis. Okay, so let's start with the randomized algorithms. Now, what's randomized algorithms? Earlier, what we did is the following. We say, okay, I have a bunch of input, and then based on this input, I make one decision, right? Okay, so either I do this way, always this way, or I do that way, and always that way. So randomized algorithm says, even if on the same input, I may make different decisions. For example, with probability half, I do this. With probability half, I do that. So if I do this, then sometimes the running time will be very long. Sometimes I can get the answer very quickly, right? Okay, so in randomized algorithms, there are mainly 2 types of them. One is Monte Carlo algorithm, the other is Las Vegas algorithm. Okay, so you see that Monte Carlo is well, famous scientist. Well, I remember it's a scientist, and Las Vegas, you see, it's a city, right? Okay, now, so these 2 types of algorithms, one of them, the running time is fixed, but the performance is on average good. This is Monte Carlo, all right? So you have fixed period of running the program, but sometimes your performance is good, sometimes not good, okay? And then Las Vegas is on the other extreme. It says, okay, I will guarantee the performance, but sometimes the running time is short. Sometimes the running time is long, all right? Okay, so this is a high-level idea about these 2 algorithms. Now, one very classic example is the following. If I give you an array with n elements, and I tell you half of them are A, half of them are B, all right? Okay, now I ask you to design an algorithm to find an A, all right? Okay, so how to find it? How to do it? So, so before we talk about the solution, you know that well, we must have some random decisions here, right? Random decision. So, or this is a bit well, A and B seems a bit misleading. So let me just re-explain the question in the following way. Okay, so the question is well, imagine A and B are just well, 2 sides of a coin, right? And you toss a coin. Well, so that one probably will be easier to think about when you, well, go along one direction. Okay, so let's see. Now, let's look at the Las Vegas first, this one. Okay, so this one says performance need to be achieved, and then running time can be different. All right, okay, so let's see. If you have so many elements, if I'm doing a randomized algorithm, and then it's just like I randomly pick an item, right? I can randomly pick an item. And what's this item? I don't know. It can be A, it can be B, half chance, right? Okay, so Las Vegas says the following. I will take a random item, and this item has half chance. Half chance is A, and half chance is B, right? Okay, and then you know, well, this algorithm, in order to find an A, you need to try many times, right? Every time you have half chance being A, half chance being B. If you have B, you will do what? You will continue, right? Because, well, your goal is to find an A. So I continue doing this. As long as I see it's a B, I keep trying, right? So with some probability. For example, I guess every one of you knows that the probability to get the A at the first try is what? At the first try, you randomly pick one item. Yeah, it's half, right? Very good. Okay, so at first try, you get A, it is half. And how about the probability that you get A at the second try only? And then what's the probability? Yeah, very good. Okay, so then see half times half. Well, but these two halves have different meanings, all right? So Wing-Chong, do you agree? So these two halves, they have different meaning. The first half means you didn't find an A, right? You find a B. The second half means you find an A, right? Okay, so basically you see that by one toss, you find an A with probability half, right? This is a one, so only one try with this probability to find A. And how much probability to find it in the second try? It'll be, it'll be 1/4, right? And the third try, it'll be 1/8, etc., right? Okay, now you see that there is a chance that it takes you a lot of times to find an A, right? So that explains the rationale of Las Vegas, right? So Las Vegas says, okay, I can guarantee you will eventually find A, but sometimes it will take a lot of time, right? It will take a long, long time. But this probability of taking this long, long time is very small, right? Okay, so in expectation, so anyone know, can compute very quickly, what's the expected number of tries to get an A by using this algorithm? So it will be 1 times half, right? This once. Twice find it, it'll be times 1/4, right? And then 3 times this, right? Okay. And continue, right? 4 times it'll be 1/16. So what's the sum? That sum will be the expected number of tries, right? Okay. Yeah, so let me do a computation. Yeah, so Xuezhen said that it's 2. Okay. Well, there are many guesses. Well, but anyway, I think that you are able to compute it. All right. It's also something not taught in this course, maybe in some earlier courses. So now at least the first 2 items already add up to 1. So less than 1 is not possible, right? It's not less than 1. And actually, you can do some trick to compute this one by letting this S be equal to this one. And then you can compute 2S is something like this. And then you do subtraction. And then, yeah, so like Wing-Chong and many Siri and also Xuezhen said, it will approach to 2. Okay. Okay, so Detlef, you are raising a very good point. That's also why I say my example I give you here is not very accurate, because this example, after you see a B, then I do not need to worry about this anymore. I just pick in the remaining elements and have a higher chance of finding A. You are totally right. But for the purpose of making our computation easier, all right, and pretend that we are doing some kind of oblivious sampling, okay? You randomly pick an element, if it's B, you put it back, and then you randomly pick again, because otherwise the randomness will be very hard to measure, okay, to compute. But definitely you are raising a very good point, okay? And that's also why I say that the example of coin toss would be more suitable, right? You toss a coin, well, so if you see a tail up, you have to retoss, right? But then you retoss, well, they still have an equal chance to appear, right? To appear in the as a result. Okay. Yeah. So Xinran, you have the same concern, right? So basically, well, for A and B, indeed, they are not independent. So a better way to interpret the current computation is to use the coin toss example, right? Coin toss. Sorry, tossing a coin, right? Okay. Well, so this is yeah. Or simply they are they are, well, some kind of no memory. So after you choose something, it will be put back, right? Replaceable choice, okay? Not like you take it out and never put it back. Okay, so this is Las Vegas. So now, Monte Carlo. So what is Monte Carlo? Now, before I talk about Monte Carlo, you can think about it, and I would also want to raise a questionnaire to see whether you understand the analysis or the reasoning of Las Vegas. This one kind of a repeated sampling argument. Oh, great, very nice. So thank you. I will. So this is basically very dominating fraction. Okay. Yeah. Thank you. So now Monte Carlo. So can anyone tell me what is Monte Carlo in our setting? Very good. Okay, so Monte Carlo is just picking for a fixed number of trials. Okay, so you just toss for several numbers. Okay, all right. Yeah, for example, I toss k times, right, or 10 times, right, and then I try to see whether you have an A. Okay. Now this one, you see, so running time is fixed because you have you tossed for a fixed number of times, right? And then performance is on average good. Okay, so because there is some chance that you didn't see any A, right? But there's also some chance that you see an A. So the performance is on average good. And actually for Monte Carlo, I guess we could also somehow change our objective to be to select as many A's as possible, right? So when you count the total number of A's you selected, then on average, the Monte Carlo, so try, for example, 10 times, right? Try picking 10 times and then I stop, right? I just complete within a fixed number of trials, and then the average number of A's I see is pretty good, right? So this is the rationale of Monte Carlo, okay? And then Monte Carlo algorithm can be used to measure the area of a irregular shape. So this is a very famous example showing you. Okay, so suppose I draw a very strange shape. I ask you, what's the area of this shape? Well, what do you think you can do? So in the textbook, there's a very standard or classic approach. Okay. Now they say that, okay, you have an area, so I yes, yeah. Both of you are right. So randomly pick a position to check. But what position picking? It seems a bit mathematical, right? And Xiyan said throw beans and count. Well, that's good, right? So actually, the example, so throw beans is also very close to the textbook answer. The textbook answer says, okay, you can throw a needle or a very tiny needle and then try to see where it lands. If it lands inside, you count once. If it's, short lines, very good. So Anya said the short lines, it's just a needle I mentioned, right? So you have a very tiny needles, and then every time you throw a needle, and then if it drops inside the area with a toss, you count it once. And if it's outside the area, now of course you need to have one reference. So you need to have one big possible area that the needle may drop, right? So you just toss, and then you count how many times it's inside this area, right? How many times it's outside? Then the area will be computed according to the proportion, right? Or percentage of time your needle lands inside this irregular shape. Okay, so this is this is where the Monte Carlo method originally comes from. Okay, well, so so I guess for randomized algorithm, I would just stop here. All right, so basically you need to know, well, this is the Las Vegas or the Monte Carlo, right? But actually, well, I probably will go into that again a bit later. Okay, so this is the beginning, the introduction, right? So we have some other analysis later on. Okay. Now, So the next thing we'll talk about, of course, it's again randomized, right? So it's about shuffling an array. Now, shuffle array. Oh, this is a very classic task. Okay, so what do we do? Well, so you see here, we start with one array, right? And then you say, okay, what do I do? Well, for I equal to array length, I larger than 0, I minus, I basically do iteration, right? So I pick this one, and then the second iteration, I pick this one, etc., etc. And then we are trying to swap that position with an earlier position. Okay, so there are different ways to do the swapping. Okay, so there is some good way and also bad way. So the good way is you let j be equal to random dot next integer I. Okay, so it's the range of 0 to I. Okay, the range of 0 to I. These integers, I randomly pick one integer. So the first method says I choose one and then randomly swap with somebody earlier. All right. Okay. And then next iteration, I choose the second last one and swap with somebody earlier, and so on and so on. All right. This is one way. Now, using this approach, you will see that all the permutations are equally likely. Now, there's also a bad approach. The bad approach says I start from 0 to array length. So which means I have a piece per second here. I start from here, and every time I swap this element with any element in the range. Okay, so for example, my focus is here. I say I randomly pick one element from the range, the whole range, and then swap these two elements. And the second time, I pick this element, and then again, I'll randomly pick one element in the whole range and swap it. Now, if you do this, you will not see all the permutations equally likely. Okay, well, so in the class, I'm not going to go into details about this, why the first one is equally likely, the second one is not equally likely, but I would encourage you to try it. Right. This is a bit challenging, all right, because showing all permutations are equally likely is not that easy. But a bit later on, I will show you some other things, which is, will give you some idea about how to prove this kind of thing, okay? Now, for now, I'm only giving you some facts, okay? The fact says, if you do procedure 1, like the good thing here, then every permutation is equally likely. And then if you do the thing here, then that's not the case, okay? Oh, it seems quite surprising, right? Actually, you will see more surprising things later on. Okay, so now next one, suppose we are required to randomly choose n things, okay? Now, for example, I give you an array of elements with n elements. I say, oh, please choose k of them randomly. Well, so again, we want to make sure that each possible k combination has an equal chance to be selected. All right, because randomness, the most important thing is you make sure the chance to select any candidate or any composition is the same. And that could make the performance of the algorithm good. All right. Okay. So one very straightforward algorithm is the following. Say, okay, easy. I from 1 to n. I try to choose a random location x. If location x was previously chosen, I just skip this round and go to the next. Okay. Well, this can give you some choice of locations, but that may not give you equal likely choice of those combinations. Okay, and actually, you know, this random location, in case it was previously chosen, you need to start over. Well, but you see, you only have n iterations. How about the case when you every time you select the same location, so eventually you didn't select enough, right? Well, so now another way to explain is, well, maybe the start over means I do not go to the next iteration of for loop. It just means start over. I just start from here, right? So that basically means every time, right? So I have altogether n iterations. In each iteration, I randomly pick a location, all right? If this location is not chosen earlier, that's good. I pick it, right? If it's already chosen before, I repick on a random location. I just keep doing this until I succeed in picking a different location. So it's something like now. So now I would like to say, well, there's one bonus point. Okay, so for the procedure inside the for loop, is it Monte Carlo or Las Vegas? Oh, good. Okay, so I see. Okay, now. Yeah, thank you. So I will stop now. Yeah, please. Yeah, I know you know it. Okay, so it seems that it's too easy, right? Because yeah. Well, anyway, that's good. You know that we will need to really find a different location before we go to the next iteration, right? Okay. Well, so now this one probably I would choose as a whole class one. Huh? It's very so it's a bit easier. Okay, so now this method, it seems okay, right? Eventually, it will give you a selection of n distinct locations, right? But the question is, can you do better? Can you say, guarantee each position has equal chance to be picked in the n distinct locations? That is a bit challenging. Yeah, so Ziao said that we can also draw from the remaining locations. But again, well, drawing in the remaining locations, the probability will be different. Okay, so I guess what I guess you know what I mean, right? So basically, for example, you say I pick two locations, right? I pick two locations out of 100 locations. Okay, and then okay. Now, very good. I see many suggestions from you. So basically, you can see that for example if you choose the first one, right, the first element, and then the probability is something like 1/100. In the second one, it becomes 1/99. So there is some tricky thing here, which makes the probability not that equal. And then and also I see some suggestions like pick n locations at once, right? Oh, that's okay, but that complexity is too much, right? So Wing Chun said, I just pick all the n locations. I choose, for example, because you have many possible combination of n locations. I choose one of them randomly, right? But you see, the number of the combination or the composition of n locations, this combination will be exponentially large, right? Because you have many possible combinations, and then it will take you not polynomial time, right? So it'll be exponential time to make everything fair, right? And then Dutleff says that we can use Monte Carlo, choose a few, and check whether one is distinct. That's also okay, right? That's also a possible approach, but it may not always succeed, right? So there's some chance of failure, right? Yeah, and then Sri said that we can borrow the idea of generating permutations and swapping the chosen position to somewhere else. That also seems fine. This seems good, but that one, the Rani, so basically, yeah, that one may also work. That may also work, but the analysis may not be that easy, right? Okay. Okay. Okay, and then I see, yeah, the values in the array can be considered to be distinct. Yeah, and then also saw Ziao that you are calculating something. Well, very, very nice. And actually, we are going to talk about one method. Okay, so we'll talk about one method which comes from the classic book of Knuth. So I believe that many of you know the famous book by Knuth, right? Art of Programming. Yeah, so basically that example is really, really amazing. Okay, so this is the generator, all right, the generator function, picking n items from m numbers. Okay, and then what is done here? Okay, so actually it is a very easy process, but the analysis is very elegant. It may coincide with some of your the answers proposed by some of you. Okay, so basically it's a for loop. It's a for loop, and then you need to call a random function for sure. All right, and then so what it says is you are trying to pick m items, right? Pick m items from n. So it's a bit reversed. Okay, so you're picking m items from n numbers. Okay, and then you see this is number 1, 2, 3 until n, right? You're picking m numbers. So it calls a random function and then divide by n minus I. If the number you selected or you chose by the random function after percentage, after taking the remainder, is less than m, then you select it. You select this I. Otherwise, you so after you select this item, you will decrease the number of m by 1 because, well, altogether your target is to select m items. Okay, remember, m is the number of items you want to select. Okay, your target, and then n is the total, is all the candidates you have. Okay, this is the number of candidates. Okay, so here you can prove every element, if you follow this procedure, every element has the same chance to be picked. Okay, well, so now let's work together to compute the probability. This is very interesting, actually. Okay, so we just use well, simple examples to compute. For others, you may try by yourself. Okay, so suppose you are your first item. Okay, so let's look at the first item. The first item, n minus I. So the first round, I is equal to 0, right? And then this is inside is n. Okay, so it means that something percentage n is less than m. Okay, so what does it tell us? Percentage n, so some random number, right? Random number, percentage n is less than m. So in this case, I will output this I, right? Because remember, I at the beginning is 0, right? 0. So what's the chance that 0 will be picked? What's the probability that 0 will be picked? 1? Okay, it should be m over n, right? Because m is smaller than n, remember? Okay, so for example, n can be 100 and m can be 10. So yeah, very good. Okay, so if your sampled value is less than 10, you select, you output 0, right? If your sample value is larger than 10, I do not output 0. So 0 has a chance of m over n to be selected, right? Now remember, this is a loop. So if 0 is not selected, in the future, will 0 have any chance to be selected? No, right? Okay, so basically, you finish this round, then 0 will be gone, right? If you do not select 0, 0 has no chance to come back at all. Okay, so basically, the probability to select 0 is m over n, exactly, right? Okay, so now I guess it's a time to do a easy questionnaire. All right, so do you follow the argument about 0 is selected with probability m over n? So still some of you didn't get. So maybe I will very briefly repeat. Okay. So basically, what we are doing here. Yeah, Sri, you are right. We are finding combination, not permutation. You are right. So I guess the major obstacle of understanding is here, the percentage one. Okay, so 0 just means in round zero. In round zero, you are selecting a random number, and this random number can be from 0. Oh, maybe sorry, can be from 1, 2, 3. Actually including 0. Okay, 0, 1, 2, 3 up to n, right? Up to n. So basically, your sampled value can be anyone, 0, 1, 2, 3 up to n. And as long as this sampled value percentage n is less than m, which means it's 0, 1, 2, 3 up to n minus 1, right? If you are these values, then you will do if. You will do the two statements here, print I. So basically, you will select 0, select the round 0, right? Select this 0. So basically, if your n is 100, this is n, m is 10, then you will be 10 over 100 chance that your sample value is less than m. Okay, right? And then with that probability, right? So the probability is 10 over 100, which is m over n, right? With that probability, your condition, your if condition will be true. And then if your if condition is true, you will select I, right? You'll print this I. So that's why we say 0, right? Because at the first round, I is 1, as I is 0. So you will have this probability making this statement be executed for I equal to 0, right? So round 0, you have probability m over n to make the if be true. And then you will print this 0 in the round 0, right? Okay, so this is the first part. Okay. Now we'll so I hope that is better after I explain. But well, so just make the whole thing smooth. Okay, so let me answer some questions so that maybe you have better understanding. Is the index of the number in M that we are choosing? We are choosing from 1, 2, 3. We are choosing from 0, 1, 2, 3 up to n minus 1, I think. In this program, we are choosing from 0, 1, 2, 3 up to n minus 1. Okay, so we are choosing these indexes. And after several iterations, probability will increase. How can we say it is randomly choose? Okay, Xinran, we are going to that very soon. How can we guarantee that exactly m numbers are chosen? Oh, okay. How can we guarantee exactly m numbers are chosen? Because whenever you choose a number like this print, you will decrease m by 1. When m reaches 0, you will no longer choose anything. So basically, you choose 1, the quota is decreased by 1. So I hope that I answer your question, Wenchong. Okay. Okay. Yeah. So now let me poll again. Now, is it okay about the chance that 0 is selected, or round 0 will have a print 0 happening with probability m over n? Okay, so now this time it's much better. Great. Okay, so let me just close the polling. Okay, Jianchong, actually there's I guess, Jianchong, you have some misunderstanding. You say that when m numbers remain, there are still m numbers to be chosen. The probability will be 1. Oh, okay. So do you mean that originally you have m numbers, and then you also choose m numbers, then the probability would be 1? Yes. Then of course that would be 1. That's sure. But remember, we are choosing from a larger set, right? We are choosing from a larger set n. Okay. Well, so let's just try to appreciate the most beautiful part of this design. Okay, now let's see what's the probability that 1 is chosen. How to do that? How to calculate that? In other words, what's the probability that after you enter the second round, right, round 1, then 1 will be chosen? Oh, 1/11, so concrete. Okay, so I see many of you are giving me some probability, which is good. And actually, it corresponds to different cases. And as some of you have already noticed, let's just write down the probability, okay? So remember, whether 1 is chosen or not depends on whether 0 is chosen or not. That will make a difference. If 0 is chosen, when you go to round 1, the m becomes m minus 1, right? If 0 is not chosen, when you go to round 1, m is still m. Your quota didn't drop. So we need to differentiate between two probabilities. So there are two cases. Let me erase the writing first. So there are two cases. First case, case 1, 0 is not chosen. This is easy. Why? So if 0 is not chosen, then when you go to round 1, it's still m. Well, sorry, it's not still. Okay, so it will be m over n minus 1, right? The probability is this. Why? Because you see, when you go to round 1, this I is 1, right? So you have n minus 1 below. So the probability that 1 is chosen becomes this, because you have one less number, right? One less thing, right? So it becomes n minus 1 now. So when 0 is not chosen, the 1 will be chosen by this with this probability. And then you need to multiply it by, so I see some of you already wrote the answer. So if you need to multiply it by the probability that 0 is not chosen, right? So the probability that 0 is not chosen is n over m over n. Is that right? Because the probability that 0 is chosen is m over n, right? So it's not chosen, it's this. Okay, so this is the probability that 0 is not chosen. And then you multiply the probability that under this condition, 1 is chosen, right? Okay, good. And then the second case is 0 is chosen, right? And then this probability is m over n. And when 0 is chosen, what's the probability that 1 is chosen? Still, this n minus 1, n minus I becomes n minus 1, right? This is still true. How about here? It becomes n minus 1 because you chose 0, so your quota is decreased by 1. Okay, so what's the result? So you see, the result is n minus m times m, right? Plus m times n minus 1. So m squared is cancelled. It becomes n times m minus m, right? So it becomes n times m minus m. And below, it's n minus 1 times n, right? Okay, so you see, you have a common factor of n minus 1. This is n minus 1. And here, you also have n minus 1, right? So after you cancel that, it becomes m over n. Same, right? So it seems to a miracle, right? Well, it's very, very elegant, as some of you say, right? Okay, great. So this is the example coming from the Knuth's paper, all right? So you see the program itself is very easy. The analysis is not difficult, but it's very elegant, right? So every number you can show the probability of choosing it is m over n. Okay. Yeah. So I guess many of you have followed the analysis, and then if you have questions, you may raise it during the break. We'll have 5 minutes break, and then we'll come back again. Okay. And we're about to, I guess I will probably move on a bit. So maybe not this one. This one I will explain in the next hour. Okay. Yeah, we'll come back in 5 minutes. Yeah. So I really hope that you would enjoy doing those analysis and then finding the beauty in the design, right? So because that's the core part for computer science too, right? Okay, so in-class exercise, let me just double check the date I set for the in-class exercise. Okay, so the date for submission will be this weekend. I purposely set that date because there's one more question in today's lecture, which is counted as in-class exercise. Okay, so I cannot, that's why I didn't open the submission yet. The submission is from February 18th. You can do it tomorrow. And also, well, I need to apologize a bit that up to now well, it's a all 3 hours lecture, all right? So no tutorial time. But at some later time, when our topics are not so dense, then we will have some explain something, some exercises or questions in the 3 hours session. The deadline for the first half will be week 7. Yeah, it'll be week 7 in 2 weeks' time. Yeah, so first half, Jiang Peng asked, first half in-class exercise includes 4 questions in tutorial 1 and 1 question which I raised earlier, and then 1 question today. But the 1 question I raised earlier, I already forgot what it is. Okay, well, I will see your answers. Okay, yeah, you can submit tomorrow if you finish everything, because all the questions are there, right? After today's lecture, so it should be easy, right? Now, if you already finished them, then feel free to submit tomorrow. Okay, yeah, the first one I remember is some kind of also finding some examples, right? Finding some example. Yeah, I guess that if you forgot about that first question, then you need to go to the lecture. Anyway, it's called in class, right? So just to make sure that, well, it's a kind of attendance purpose, right? And about the bonus, actually, well, because as I said, the one earlier is seems that it's pretty easy, but still, I guess I will be fair a bit. So I will, considering the typing speed, I will give bonus to the first 10 students. Okay, so we'll start. Let me see. Okay, there's also a question about the bonus. What's the maximum bonus you can get? Every one of you can get. This current max is 5, but I set the maybe up to 10. So well, that will change real time. Okay, so it, this part will somehow depend on the performance of the midterm and also assignment, because if the midterm and assignment well are pretty good, then actually that much bonus is, well, will just overflow, right? So let's just see the performance of the midterm before I decide whether it's 5 or 10. Okay, so currently it's indeed 5. Let me, okay, so let me continue with this so-called stupid sort. Now, I guess everyone knows sort, right? So there are many different sorting algorithms. But now, today, I'm going to talk about very stupid sort. What is this? Well, it says that I do a while loop. Okay, I do a while loop. And I check whether this array is already sorted. Well, checking array, whether the array is already sorted, it's easy, right? Because you just need to compare adjacent numbers to see whether the next number is larger than the previous number. Well, that's can be done in linear time. Now it says, okay, if it's not sorted, then I shuffle the array. Well, this seems kind of a very weird operation, because, well, this shuffle has a very low chance to give you a sorted array, right? But anyway, the algorithm is doing this. So how good is this? Well, how you can see that actually there's a comment about it's actually the worst algorithm you will ever use, right? But although it's worst in running time, you can the good thing is you can analyze it. Okay, you can analyze the running time of this algorithm. Oh, that's still good. Let's see what we can do. Okay. Now, suppose that we are assuming some kind of good implementation of the function call, and then you see checking whether the array is sorted is linear time, as we mentioned, right? And the shuffle, we have a good shuffle earlier, which also take linear time, because you do iteration, right? N positions, each position do one shuffle. That's easy. And altogether, there are n factorial possible arrangements or permutations of the array, right? And then, so the shuffle, right? For the shuffle to get to the right answer is 1 in n factorial, right? So suppose that elements are unique, right? So that every permutation is different. So now, if something, the odds, right, of getting it is 1 in something, in x, then the average time we'll wait is x, trials. Okay, now this has something to do with the Las Vegas algorithm we talked about before, right? So remember, we talk about you toss a coin, then how many times you need to toss in order to have an A, right? Or have a heads. Now, at that time, we know it's 2, right? Now, well, but you know, the probability is 1/2, right? Getting an A is 1/2 in each trial. Then on average, in expectation, you will need twice to get that ideal output, right? Okay, so basically the whole running time will be test plus shuffle times n factorial. That is 2n times n factorial. It's roughly this. Okay. Well, it's bad, but it's still bounded, right? You have some chance. This chance, in expectation, you need factorial time to get the final result. Well, but it's better than doing nothing, right? Okay, so this is one thing. And now comes the today's in-class exercise. Now we know in our previous lectures, we talked about the so-called knapsack problem, right? And the knapsack problem, every item has a size and a profit, right? And you have a bag with a certain size. And then the question is how to pick items with a size budget and try to maximize the profit, right? Okay, so I hope you still remember this setting. Okay, now let me just quote again. Everyone okay with the setting of knapsack? What's the knapsack doing? Still some of you are not okay. So remember, you have a bag with a certain size and you have a lot of items. Each item has a size and a profit, right? And then you need to put those items into the bag so that the bag size is not exceeded. You cannot put in more, right? You cannot put in items whose total size is beyond your knapsack size, all right? So within that limit, you try to maximize the profit of all the items inside the bag, okay, inside the knapsack. Okay, so I will not do a second polling. I assume that now it should be relatively clearer. So okay, so now what's our suggestion? Now remember, knapsack, we have many methods, right? Many methods, but the problem is today this slide, its focus is randomized algorithms, right? So what can we do for randomized algorithms? Well, here is one possibility. It says, okay, we start with a greedy solution. Remember, greedy solution is not too bad, right? Greedy solution is some kind of approximation if you combine it with another approach. So greedy solution is a fine solution, all right? So greedy means you every time take an item which has a biggest ratio of profit over size, right? So this is greedy, right? You try to say pack the most valuable per size item, okay? So now, where does the random come from? Random says, I randomly choose an item from the knapsack, okay? I replace it with other items. How do you replace it? It doesn't matter. You can use also greedy or other algorithms, right? So for example, I say, I remove this item, then I have a bit more size, and probably using greedy, I can do better, right? Because I already removed one item. That item, I will not, at least that item will not go into knapsack in this round. I will not consider it, right? I just consider this item to be temporarily unavailable, right? So I remove one item and then use a greedy algorithm or other algorithms. Anyway, I try to put them into knapsack, right? To see whether now I have better profit. Okay, now if this result is better, keep it, all right? Otherwise, you forget about this solution and just go back to the original solution and try to do random thing again. Okay, so clear about the algorithm itself. Let me just do a polling again. Yeah, because this is in-class exercise, so I need to Oh, okay, very good. When do we stop? We stop if you cannot improve the current solution, no matter which item you remove. So remember, you remember that for the knapsack, right? I draw a knapsack. Okay, you have a bunch of items in, right, inside, and then say, okay, I randomly pick an item, I remove it, and then I put in some more items to make it better, right? So if this is not possible, I consider another random element, right? Remove it, try to, well, put more things in to see whether it's better. So if removing any item is not possible to make the knapsack better, okay, then I stop. Because by using this approach, I can no longer improve, right? Because I've tried all the single item in my current solution, right? Okay, so let me just, sorry, bother you again. So after I explain this, is it better? Now do you get it? The algorithm itself, when does it stop? And each round, what do you do, right? So you pick a random item, you try to, you throw it away, and then you try to put in something using some algorithms, okay? You try to put in something, and then you try to measure whether the new solution is better. If yes, I use the new solution to replace the old solution. If no, the new solution, just forget about it. I try to handle the old solution again. Okay, the difference between random pick and iterate over all items. So random pick sometimes will be faster. If you iterate, you try all the possibilities, then maybe the first many possibilities, they have no chance to improve. So you are wasting time checking those, right? So random is just trying to improve your running time in the expected sense. Okay, so I think that okay, so hope it's fine. So now what's my question? It's an in-class exercise. So the in-class exercise is, can this method always produce an optimal solution for the knapsack? Let me repeat. Can this procedure, can this algorithm always output the optimal solution for the knapsack instance? Okay, so this one, no, okay, very good question. If you say yes, then you need a proof. Okay, if you say no, then you need to give me one example. In that example, following this process, you will not get an optimal solution. So clear? Now let me do a polling. Yeah, you're right. Zia, you're right. Anyway, you need a proof. One proof is a mathematical proof. The other one is proving by an example, right? You show me one example where following this process, you would not get an optimal solution. Okay. Yeah, so I noticed that still some of you didn't understand the question itself. Well, then in that case, I guess that probably can review what knapsack is. But for this current one, I think that, well, the procedure is quite straightforward. It's kind of local search, right? You have one solution, and then you say, okay, in this solution, I just try to do some minor change, right? I remove one item. Remember, remove one item, okay? And then I try to see whether for in the remaining unpacked items, I can pick some of them to make the current solution better, right? If yes, just do it. If no, then I will take the removed item back. Okay, try to remove another item. So basically, well, you are comparing the new solution with the solution, the old solution where no item is removed from that solution. Okay, so solution one Okay, solution one, the solution one. And another solution is you take one item out, you put something in, it becomes solution two. If two is better than one, you use two to replace one. Okay, so now two becomes the current best solution. The current solution, not best, the current solution. So Wing-Chun, what do you mean by do we check newly added items? Replaced one. Oh, okay. I roughly get your point. So basically, you have a so-called current solution. Current solution, every item has the same role. Okay. So whether they are newly added in the earlier rounds, it doesn't matter. They just belong to the current solution. So if we get a better solution, you will continue. Yeah, you will continue. Until you cannot get a better solution, no matter which item you remove. Okay. So Jiang Kun, what we are doing in this exercise is, if you think this process can give you the optimal solution in some step, always, okay, always, then you need to prove it. Otherwise, you say, oh, not always. Sometimes, no matter what I do, right? So sometimes there is one instance where if you follow this algorithm, when you stop at a solution which is not optimal. So replacement, very good question. Okay, so Jachi asked, is the replacement only one-to-one? No, it's one-to-many, which means you remove one item and you can add in a few more items. Okay, so in other words, you can use two items to replace one item in the current solution. Yes, you're right. So you're right. Prove or falsify this the optimality of the algorithm. Okay. Yes, you're right. If a better solution is found, then you will do this whole process again. You check every item to see whether removing one item and putting in more will give you a better solution. Okay. Okay, thank you. Yeah, so basically, before I continue, I need to clarify something. So for in-class exercise, as I mentioned, I will not mark it seriously, but I hope to see some nice logic, especially the two questions not in tutorial one. Okay, tutorial one questions, they are, well, at least the first three questions are pretty standard, pretty traditional. Okay, but the other two I raised really in class, they well, deserve a bit more effort. Okay, right. Okay, so now I'll move on. So now let's look at one more example about randomized algorithm to see, well, what can happen. All right, so when you have this strong tool of randomization. So here it's called a minimum cut problem. All right. So what is minimum cut? Yeah, here you have a graph G whose vertex set is V and X set is E. And then, so let me draw something. Okay. So you have many edges. Okay. So you have a graph. And then you want to output a cut such that the number of edges between or in the cut is few as possible. In other words, we are trying to find a min cut, minimum cut. Okay, so what does it mean actually? Well, cut basically will divide the vertex into two subsets. Okay, you may say, okay, this vertex, this one, and this one is my red collection. Okay, and then I also have another collection like let me see the color. Yeah, blue one. This is blue one. This is a blue one. Okay. Now, if you have this kind of cut or division, then what edges are the cut edges? Basically, this one, this one, this one, this one. So which means any edge whose two endpoints are in different subsets of your cut. Okay, so in our case, if one of them is red, the other is blue, then that edge is a cut edge. Okay, and then we try to find a cut to minimize the number of edges or number of cut edges. Okay, the number of cut edges. Okay, now again, let me see whether you understand the question first. Okay, so is the question clear? You have a graph, you divide the graph vertex into two subsets, and then you try to find a division such that the edges connecting different subsets, that number is as small as possible. Okay, as small as possible. Okay, yeah, so for those who voted no, all right, so can you tell me which part you are not clear about? You can send me private messages too, because I really want to make sure that at least for the problem description, you could follow. The later on analysis, some of you cannot follow, it's fine, all right? Because anyway, you have some chance to review. Okay, so I'm expecting some questions. Oh, very good. So Wenjong, you are giving me a very, very good suggestion to explain this in an alternative way. Okay, so yeah, indeed. So this problem is equivalently termed as the following: how many edges you should remove in order to disconnect the graph so that the graph is split into at least two components. You will remove certain number of edges, right? Okay, for example, the 4 edges now here in the figure. And then after removing these edges, the whole graph becomes disconnected. So they form separate components. For example, if you use the traditional searching method, DFS or BFS, they can no longer reach the whole graph if you start from any point. So that's the solution we are targeting for. Okay, so we are trying to remove the minimum number of edges to disconnect the graph. Okay. Okay, so now I hope it's better. Let's see whether now you understand the problem or not. Okay, well, so this time at least it's much better. Although, well, very tiny proportion still do not understand, but it's much better. Yeah, so thank you, Wensheng. A really very nice suggestion. Okay, so anyway, I guess I still need to move on, and then we try to find out the solution. So on the way of finding the solution, you may, well, have a better feeling for the students who still didn't get. You may have a better feeling about what we are doing here. Okay, yeah. So actually, we also have this equivalent interpretation right here. Now, for min cut, right? So in this graph, ABCD, and then the minimum edges to remove to disconnect the graph is these 3, right? Okay, and then you know that the min cut, the size of min cut will not be larger than the smallest node degree, because for example, if you say I have 1 node, his degree is 3, then the worst case I just remove all 3, then this node will be isolated, they will be out, right? So the whole graph will be disconnected because D is gone, right? D is separated from the whole major island, right? Okay, so the min cut size will never be larger than any node's degree, right? Okay, well, so this is interesting. And then what's the algorithm? So the algorithm says, while you have still more than 2 vertices, then I will pick a random edge from E and contract the edge. And then in the end, okay, in the end, you have only 2 nodes remaining, because whenever you have more than 2 nodes, you will do this, right? You will pick a random edge, contract the edge, and then in the end, you have something, right? In the end, you have 2 nodes. They are somehow connected. And then now you say, okay, I'll break it. And then these 2 parts are separated, right? And then, of course, you try to minimize the edges that cross these boundaries, right? Okay, so that's the high-level idea, all right? Now, contract, what does it mean by contract? Now, I will give you one example. Say you have a triangle, right? A triangle, and you say, okay, I choose these 2. I choose one edge. This one edge. I say contract it. What does it mean? It means that I combine these 2 nodes together. Okay, the 2 end nodes. I combine them together. These 2, this go here. Eventually, it becomes the graph up, right? And then this node will represent 2 nodes in the original graph. These 2 nodes. Okay, so contract just means that edge I choose not to cut. Okay, so these 2 things will be merged into one single identity, one single node. Okay. All right. So let's do some analysis. Now, about the algorithm, contraction seems a bit difficult, but I just, well, I give you one example, but maybe that's not enough. So I'm just trying to see whether the algorithm is clear. So algorithm itself is clear. Every time you randomly pick an edge, and then you try to put the 2 nodes of that edge together, they become one thing, all right? And then, well, the remaining graph didn't change. But actually, there are quite some students who didn't understand the algorithm yet. So let me just well, use one more example, because that example I gave you earlier is too easy, right? Too simple. So let me give you one more example. Okay, so this is one example. Suppose it has edge here. Okay, so I say I pick this edge. I pick this blue edge, and then the consequence of this contraction is the following. I draw a figure here. It's a new figure after contraction. Okay, it's fine. Okay, so this is 1, 2, 3, 4, 5. It's 1, 2, 3, 4. Okay, so basically 4 and 5, they become a single node, right? They're merged, right? Because this edge is contracted. So 4 and 5 go together. And then what's this new node's connection to the other nodes? Well, as long as one of the 5 and 4 have a connection to the other node, then that connection will be there in the new graph. For example, there is an edge from 4 to 1. So as a union node, this node also has an edge to 1. There is an edge from 5 to 2. So as a union node, it also has an edge from 4, 5 to 2, right? And there is an edge from 4 to 3. And as a union node, it also has a connection to 3. So as long as one of the 2 nodes has a connection to another node, then in the new graph, this combined node also has a connection to the other node. Okay, so this is the way to do contraction. Okay, so I hope that it's better this time. So this time is okay about contraction. Great. Okay, thank you. Now let's continue. All right. So what's the algorithm? The algorithm is doing every time randomly pick an edge and contract that edge, right? So so we need to do some analysis. The analysis says, suppose C is a minimum cut. All right. We need to analyze the chance that an edge in C is contracted. Okay. So what does it mean? Well, it means the following. Suppose, because minimum cut, minimum cut, the number should be small, right? For example, if you have 100 edges altogether, maybe the min cut only has 10 edges, right? It's very natural. So min cut only has 10 edges. You altogether have 100 edges. So if you randomly pick an edge, that edge should have a very small chance to be inside this 10. This you agree, right? So because, well, let's just, well, imagine, right? Your min cut is very small. Okay, so the randomly picked edge will have a small probability of being inside the min cut, right? Or in other words, you have a large probability for a random edge to be outside of C. So if a random edge is outside of C, then it's very safe to contract it because, you know, our algorithm in the end will give you a graph with two nodes, right? And any edge between the two nodes, there are edges not contracted. So as long as your cut edges is not contracted, then your solution is good, will be correct, right? But of course, you need to make sure none of the cut edges is chosen in your algorithm, right? So let's see that probability. Okay, so let's see. Now, so yeah, so basically we worry about the one thing. One is the final result, is it a cut of G? And the answer is yes, right? Because if you have two nodes, right? Two nodes drawn here. So any edge between them, if you do this cut, then of course these two groups are separated, right? So it's really a cut. And then what we worry about is what is the probability we find a minimum cut, right? Okay, so let's see. So firstly, how many edges do we have? G. Oh, easy. It's just the size of E, right? And then it's equal to sum of all the node degrees divided by 2. So this one is easy, right? Because every degree contributes to only one side of the edge. So if you sum up all the degree divided by 2, it's the number of edges, right? So altogether, it will be larger than or equal to n times the min cut over 2. Okay, because we said the min cut size is less than node degree, right? Okay, so every node degree is larger than or equal to C. So if you sum up all, it will be larger than or equal to n times C, right? And then that's the value, the number of edges, right? Number of edges is at least n times size of C over 2, right? Okay. And then the probability that a random edge is in C is less than this. Okay. Why? Because the probability is what? The probability is what? C over E, right? Okay. So C over E, what is E? E is larger than this. So C over E should be smaller than C over this, right? So it's smaller than or equal to 2 over n, right? So this is the probability that if you randomly choose an edge, this edge is in the cut. Okay. And then we need to say how many iterations do we do? Okay. So we have quite some iterations, right? Because we need to reduce the number of nodes from now. Each time we contract one edge, right? Each time we contract one edge, we are merging these two vertices together, right? So if you're merging the vertices together, the number of vertices will be reduced by 1. So you cannot do it too many times, right? You just at the very beginning you have n vertices, right? And then after one iteration, you become n minus 1 and becomes n minus 2, right? Yeah. So yeah. So each node they have at least C degree. You're right, because we mentioned that the graph, right? You always have a cut solution which just cuts one single node out. So the min cut must be smaller than or equal to the degree of any node, right? You will never need more than that number of edges to disconnect a graph. So that's why C is the lower bound of the degree of any node, all right? Node degree need to be larger than or equal to C. Okay, yeah, good. Now, you see, we contract one edge, you combine two nodes, and then the number of nodes is decreased by 1. So after one iteration, you will have one less node, and then and so on, until in the end, you have two nodes. So basically, you only have this many iterations. You don't have more, right? Okay, each iteration will go to the next stage, right? Okay, so let's see. The probability that in the first iteration, this edge is not in C is larger than this. Because earlier we say the probability that this chosen edge is in C is at most 2 over n, right? So let's go back to the page here, right? Because this is at most 2 over n. So the probability that it is not in C is at least this one, right? It's at least one. Now, second iteration, the probability is at least 1 minus 2 over n minus 2. Because in the new graph, you have one less node. You only have n minus 1 nodes, right? So the probability will change a bit, right? Okay, now this time, we are really doing this adaptive change, right? You contract one edge, you have one less node. So in the remaining graph, when you pick edges, then this probability will change, right? It's no longer uniform. It will change. So now the second round, the probability will be at least this, right? Not in C. Now in the last round, the probability that this edge is not in C will be larger than or equal to 1 minus 2 over this quantity, which is 1 minus 2 over 3, because in the last round, you only have 3 nodes, right? After the last round, you only have 2 nodes. So in the last round, you still have 3 nodes. So the probability is 1 minus 2 over 3. So let's multiply them together. Okay. So what do we do? Okay, first probability, second probability, third probability, and so on, and last probability. So this is the probability of finding that min cut in your final solution, because each of them says no edge in min cut C is chosen by you, right? And this one also says, okay, in the second round, no edge in the min cut is chosen by you. So if in all the rounds, the min cut is not touched at all, then in the final solution, that cut is just min cut, right? Okay, so now you see, if you multiply all the probability together, it would be the probability of finding the min cut in your final solution. And let's see what this is. This is a n minus 2 over n, and then n minus 3 over n minus 2, 1, and n minus 4 over n minus 2, etc., etc. Okay, in the end, you will cancel many terms, and you only have this remaining. 2 over n times n over n minus 1. Okay. Well, so this is the probability of finding C. So what's the probability of not finding C? What's this? Well, so you see, the probability of not finding C actually is quite small, right? Because you know n is a huge number, right? You can consider n to be a big number. So this number is actually very small. The probability of not finding C is actually very small. Okay, but you may ask, is the best we can do? Well, okay. So let's see, we'll have something, right? So probability of not finding C in one trial is this, right? Okay, and then if you try K times, and then not finding will be this. Okay. Now, and if K is Cn squared, then the probability of failure will be less than this value. So actually, just now I'm making a minor, a wrong comment, right? I say, well, this is a very small value. Yes, this is a very small value, but we are doing 1 minus, right? So not finding C, 1 minus a small value, it seems not a very good deal, right? For example, you say, okay, the probability of not finding C is 0.99 probability. So that's a high probability, right? With a high probability, you didn't find it. Well, you may feel very frustrated. You say, then that's not good, because if I run the algorithm once with a very high chance, I will fail. But this page is trying to show you, well, do not be disappointed, because we can run it many times. As long as we run it many times, we can compensate for that, right? So if you run it for Cn squared times, then the probability of failure is less than or equal to 1 over e to the power of C. And then, well, this calculation is by this limit operation, right? So if it's 1 over e to the power of c, it's already very good, right? Because 1 over e is less than half. So your failure probability is less than half. If you further boost by running more times, then you will fail with even less probability, right? Okay. Well, so maybe you will ask me, how do I know whether I fail or not? Can anyone tell me? This is a bonus, okay? So because we just run the algorithm and have one solution, right? So how do I know I fail or not? Because if I succeed, then I can stop the algorithm. But how about if I don't know whether I succeed or not? How to address that issue? This page only tells you that, well, your failure probability after so many trials is small, right? Okay. Then, or maybe I turn my question another way. Do I need to know whether I fail in each trial? Very good. No. Why? I do not need to know. Yeah, fail means not optimal. Yes. Yes, you're right. You're right. So you get bonus. Okay. All right. So basically, you do not need to know whether you fail or not. You just need to keep the best solution among all the trials. All right. And that best solution, you just give the solution to your customer. Okay. So this is the solution I find, because this theorem tells you with a very small probability you will fail after so many trials. So after so many trials, you take the best solution of all these trials. The chance that this is not minimum is very small, right? So you can live with that. It's totally feasible, right? Okay. Yeah. So this is I believe this is the last example I have for randomized algorithms. So I think that I'm trying to give you a message that well, randomized algorithms, the major thing, you have Las Vegas and Monte Carlo, but inside you have many other tricks to boost the probability, right? So for example, this mean cut example, I'm trying to show you that by running many times, right, you can boost the success probability. Okay. Yeah, and then actually this one, you can consider it to be Monte Carlo or Las Vegas. So for this mean cut algorithm, do you think it should be Monte Carlo? Yeah, I see many Mont. Okay, so it should be Monte Carlo. Why? Because I said I run a fixed number of times, right? I run fixed number of times, but I do not guarantee it's optimal, but with a very high chance it's optimal. Or on average, its performance is pretty good, right? So it's basically a realization of kind of Monte Carlo idea, right? Now you do Monte Carlo, you say that you see that by running more and more times, you can boost the success probability, right? Okay, and also I think that in the whole session of the randomized algorithm, you have seen some very beautiful things. So that's the thing, that message I would like to bring to you. Okay. Yeah. So now we'll move on. All right. So today, I guess I will finish the streaming algorithm. For the remaining, I would probably postpone it to the next lecture. Okay. So streaming algorithm. What is streaming algorithm? Now the basic setting is the items or integers, right? So you have basically a sequence of numbers, right? So the items come one by one, and then you see it. You can store it, but well, you cannot store too many. If you can store everything, it's just the normal offline algorithm, okay? Because or normal online algorithm. So more close to offline algorithm. So basically, if you can store everything, then not a big deal. I just store everything and do computation. I can have the answer. But the problem is you do not have that many storage. Okay, you have limited storage. You cannot store all. So what can you do in some cases? All right. Now, basically here for streaming algorithms, the target is something like I would like to do some query on the given data. Okay, So suppose for example, you give me a bunch of data. I want to say, okay, please do some algorithm. So design some algorithm so that later on I can come back with a query. For example, did you ever see a 5 coming to your site? Then if you do not store 5, you may already forgot. Oh, how do I know? I don't know whether 5 is here. Then you lose, right? So basically, what you are trying to do is you try to store some useful information so that later on when people come with a query, ask you some questions, you can answer them accurately or approximately accurately to fulfill the goal. Okay. Now here, again, because you cannot store it, so if you decide not to store, then you would just lose the item. Okay, so it's a single pass model. So you can only see the items one by one from the very beginning. And then whenever you see one item, you can decide what to do with it. But after that, this item will be gone. You no longer have access to it. Okay, so this is the streaming scenario. So now let me just do a polling. Are you clear about the general background or general setting of the streaming algorithm? Okay, generally good. Can you replace stored items? Yes, very good question. So Wing Zhong asked, can stored item be replaced? Yes. If you store 5 now, and later on you see a 6, and you may choose to store 6 instead. Okay. All right. So there's still someone who didn't understand the setting. Well, that's fine, because we will have some concrete examples to help you understand. All right. Now there are many different queries possible. Okay. For example, one of the queries says distinct elements. So basically, it asks you to find the number of distinct elements that you ever see. Okay, duplicate ones, I do not count. I just count distinct ones. For example, you see 1, 2, 3, 4, but many ones, many twos. It doesn't matter. I only need to know how many different values you have seen, right, up to now. And then there are also some queries like find all the elements that appeared at least twice. Okay, this is also one query. So now, before I show you one other example, can anyone tell me one query which is very easily done by streaming algorithm? So here I'm talking about 2 queries, right? Distinct elements and find elements that appear twice. So there are some queries which are very easy to be handled. What query is that? There's also some bonus. Oh, very good. Okay, and you said find min max. Very nice. Okay, so basically, you know, if I just want the maximum value, then your algorithm is very easy, right? I have one item, another item, I compare, right? Which one is larger? I keep the larger one, okay? Throw away the small one. So by doing this, right, I can always have access to the largest one in my hand. And then later on, people ask me, what's the largest value you have seen? Easy. It's in my storage, right? I just store one number, right? And the min is similar story, right? Okay, so that's the easy thing. Mean, okay, yeah, mean is also easy. And actually, well, so I will come to that very soon. Now, the streaming algorithms actually have some applications, like in external memory, right? External memory algorithms. These are something like the streaming algorithm, but a bit different, because external memory, like hard disk, when the values are stored, somehow you have access to it later on if you want to read it again, right? But I believe that in your undergrad course, you have learned kind of sorting algorithm, external sort. So external sort has some kind of similarity with merge sort. Basically, you read items from hard disk to main memory, and then you can do kind of merge process so that, well, because the numbers can only be compared inside main memory, but main memory has a limited storage. You cannot store all, so you cannot do a whole scale merge sort. It's not possible. You can only do gradual merge sorts, right? By bringing blocks into the main memory and write back blocks to the hard disk when you finish some process. So I'm not going to explain the external sort here. If you are interested, you may go to respective references. And then also in communication, people also consider communication complexity. You try to reduce the number of communications needed in the whole process. And then there's also kind of application called sketching. So basically, you are trying to give a, now sketching means when you draw, you do not draw the whole picture. You just draw some kind of lines showing the rough picture of the image you want to draw, right? Okay, so this is the scenario where streaming algorithm will also be useful. And finally, people will care about so-called sublinear algorithm or compressive sensing. So sublinear time algorithm, what's this? So basically, usually we say linear time, ON, is already pretty good. But if N is huge, now reading through all the N also is not realistic. So sometimes you have to skip something. You cannot read everything, all right? Now, if you skip something, you have sublinear algorithm. Now you need to make sure that, well, the things I skipped may not be that important in the overall query in the end. So you need to make a wise choice. And actually, there is also some kind of, remember I mentioned to you some kind of PCP, right? Probabilistic checkable proof. So that thing also involves only looking at the proof at some selected positions. And then he will conclude, okay, this proof is correct. Well, it's some kind of miracle. Well, again, I will not cover it, but if you are interested, you may refer to it. But, well, do not expect to understand the full detail with the current foundation. You need to learn more if you are interested. Okay, so anyway, we know that you have many applications for the so-called streaming algorithm. And then now we come to the toy example I'm showing you here, all right? So this example is a bit more difficult than max-min, but also not very difficult. So we have integers from 1 to n coming in. I already told you it's 1 to n. And then I also tell you one of them is missing, but you don't know which one. And then you need to design a streaming algorithm to find the missing number. So again, it will be a bonus question. Oh, very good. Okay, so Jianchong get a bonus. Okay, so yeah, so now this time, this one is something like a speed. All right, so now the solution is also not difficult. You just keep the sum of these incoming numbers. And then in the end, after all of them come, you do a subtraction. And then you know which one's missing, okay? So like Sri said, you can also do some kind of XOR sum or something. Well, anyway, it's keeping a sum, right? Keeping a sum. And actually, it has something to do with Wing Chong's earlier suggestion about mean, right? Because sum, well, it's just mean times the total number, right? Okay, well, yeah, so this is a toy example. And then actually today, the remaining minutes, I'm trying to say something about the counting distinct elements, but I will not expect to finish it totally in this class. Probably I would need a bit more time next week to finish it. So counting distinct elements, what is the approach we are using? Okay. Now, remember, we have elements, right? So the numbers are from 1 to m, and then you have n numbers coming in. Okay, so there are n numbers, some of them are duplicate. And the goal is to estimate the number of distinct elements up to an error, because if you are not allowed to store every one of them, it's basically impossible to give an accurate answer. Okay, so you need to live up to some error. Okay, and then a simpler goal is the following. So if you are given a t larger than 0, and then you need to design an algorithm which with probability 1 minus p, it will answer yes if distinct elements is larger than a certain number larger than t. Okay, you have mildly more distinct numbers than t, and if you have mildly less distinct numbers than t, then you answer no. And each of them, you should do it with high probability. Okay, with high probability. So that's the basic goal. Okay, with certain probability, a good probability, you will output the right answer if the true answer is has a certain distance away from the correct answer. Okay, so correct answer is t, right? And if the actual distinct number is larger than the a bit larger than t, then I answer yes, because well, I'm more confident, right? Because if you ask me to directly answer whether it's t, no way, I don't know, right? But if it asks you whether it's larger than t for a certain amount, then I may have larger confidence to do that, right? And then if you have this procedure, then you can just run the algorithms for a lot of t, right? Or t equal to 1 plus epsilon, 1 plus epsilon plus square, etc., etc. Now you can solve the real question. Okay, so let's see. Yeah, I may not have more time today, but yeah, we still have 2 slides. But I guess we can cover it in the next lecture. But before that, yeah, so I hope that you can review something on bucket sort first. Okay, try to see what is bucket sort. Okay, and then in the next week we'll come back to the detailed explanation. Okay, yeah. So up to now, I guess that for the algorithm part, we only have a tiny portion left, and then basically in the next lecture we'll only use less than 1 session to finish, and then we'll go on to the game theory domain. Okay, yeah. So any question? And also, I guess university announcement says that all the exams will be online. So it's the same for our course. So on midterm and the final exam will both be online. And but we will do a rigorous invigilation. While later on I'll post the requirements for the online midterm. And all the midterms will be paper and pen written, no typing. Okay. Very good question. There are 2 questions. One is about greedy knapsack, the explanation. Oh, okay. So the greedy knapsack just means that every time you pick an item whose value over size is the largest, while at the same time it can fit in the knapsack. That's the greedy knapsack algorithm. Okay. Ratio is the largest. At the same time, it fits into the current knapsack. Yeah. Okay, good. And then about closed book, open book. Well, so I guess I need to do a polling. Yeah, for midterm, we have an option. Okay, it's either closed book or open book. And then you could expect that closed book will be easier questions. Open book will be more difficult questions because, well, you cannot refer to any notes. Oh, well, you can refer to any notes in the exam, then the questions definitely will be more difficult. So I will do a poll. Yeah, yes means open book, no means closed book. Which one do you prefer for midterm? Yes means open book, no means closed book. Okay, so basically the poll results, well, although not everyone, but I guess it's already showing something. So this is the results we get. And I guess for midterm, we'll adopt closed book. You may have a try. Okay, so yeah, so how those questions, how difficult those questions are for closed book. And then for final exam, well, you may, well, we'll vote again. All right. And then yeah, as I said, it's an online exam, right? Online closed book. Exam is week 10, as Shujin answered. Yeah, so agree that this course will be hard. But as I said earlier, midterm, the question should be easier than the assignment. That's for sure. All right, because as I said, assignment, you have more time, but midterm, you only have 2 hours or 3 hours at most, right? it's not possible for you to figure out a solution for a brand new problem very quickly. So yeah, so that's the expectation that we have. So you would also expect some questions for closed book. You would expect some questions for understanding only, not calculation, because most of the questions probably, no, majority of questions you may need to design algorithm, do some analysis, or analyze some algorithm given to you. So those may all happen, all right? And then, but for closed book exam, I will also test you some understanding of the different concepts, okay? Okay, Wenjong, I agree, okay? So since it's online, I totally agree that it will not be longer than 2 hours. I will use the other, I will use the other 1 hour for lecture, okay? So most likely it will be one lecture first, 1 hour lecture first, followed by 2 hour exam. Will that be good? Okay, good, great. Yeah, and then as I said, tomorrow you will see the first assignment. I'm still thinking about what questions to put in. Now I have already 3 questions to select from. So let me see how to balance different topics. Okay. Yeah, and remember, as you see in the canvas, we still have lecture in week 14. Okay, so to make up the lecture in last week. Yes, you're right, Chenwei, you're right. We have 6 in-class questions to do in total. You're right. This is for the first half of the semester. Again, some students ask me about invigilation. Okay, so so some of you, no, not some of you. Yeah, sorry. Although some of you have taken my course, but it's not an assessment-based course. Well, my philosophy is that I will do a very rigorous invigilation. So as I said, I will send you the how to use the 2 device later on. Okay, so basically, although I trust every one of you will be honest, I still need to be fair to all of you. So the invigilation will be very rigid. Okay. Okay, so Zhengwei, you're asking whether I can upload another 2 questions to Canvas too. Well, the answer is no, because as I said, this is in class exercise. And then actually, for example, today, when you review the recording, you will know which question I'm raising. And then in that other lecture, you will also know it after you go through the recording, or maybe you are in person in the yeah, just like you are now, right? You are in the lecture. So these 2 questions I will not post to encourage those who participate in the course. Yeah, so to be fair to you, right? So I will not post those 2 questions. Thank you for understanding. Okay, any other questions? Yeah. Today's lesson is over. Yes, it's over actually 10 minutes ago. Sorry for keeping you so long for the exam issues. Yeah. Okay. Then I guess I will stay behind for a few minutes, and then feel free to leave. And then see you next week. And hope you will find the assignment friendly. All right. Try to get something from the assignment. Thank you. Yeah, by the way, take care. Okay, then yeah, I guess all the questions are asked. Then see you next week. See you.